In this video, I'm going to talk about the stresses that are present when a beam is loaded in bending. So if we assume that we have this rectangular beam here and it experiences a bending moment sort of in this direction, so the ends are being bent down in that way, then the top surface of the beam will be loaded in tension, and the bottom surface of the beam would be loaded in compression. And in fact, we can look at the distribution of those stresses through the thickness of that beam. If we call this total dimension here h, the dashed line in the center represents the neutral axis where there's not any stress. Up here this is in tension, and down here this is in compression. Now, if the bending moment were reversed, then these would also be reversed. That's worth pointing out. We can then look also at the distribution of the stresses throughout here. So at this top surface, the tensile stress is maximum, and it decreases as we move down toward the neutral axis, at which point it switches over to becoming a compressive stress, and the magnitude of that compressive stress increases all the way down to that bottom surface. So this is the way that the stress gets distributed, and we can now consider two different specific cases, 3-point bending and 4-point bending, to look at what the expression is for the maximum stress in that specimen. Let's first make sure that we are understanding the way in which we're defining the geometry of the beam. So if this is our beam, we are going to define its length as L. We're going to define this dimension here as we did on the previous slide as H, and we're going to define this dimension here as B. And so normally we would have a beam that sort of looks like this, but whatever the geometry, these are the variables that we will use to describe it. So let's move on and look at the 3-point bend test. In a 3-point bend test, the load is distributed at 3 different points, at these 2 points at the end and 1 point in the center at the top of the beam. We will define this length S to be the span of the two. In this particular case, it's the same as the length. That's not true, though, in the 4-point bend test, which is why we describe it in that way. We are interested then in the maximum stress at the outermost layer, and so we can write an expression then for the maximum stress, and that's equal to 3 times the load times that span length divided by 2bh squared. And again, this dimension here is h, and then the third dimension of the bar is b. So this gives us the maximum stress under 3-point bending. Let's take a look at the equation for 4-point bending. Here's the geometry of 4-point bending. It's a little bit different than in 3-point bending. We still have half of the load supported at each of the ends, but in contrast now, the load on the top side of the beam is distributed in 2 different points. In this case, we define the span S to be the distance between these 2 points here. We can find the maximum stress present in a similar equation, 3 times the load times that span divided by 4bh squared, where again this dimension here is h and b is the third dimension of the bar. 4-point bend tests have some benefit over 3-point bend test, the primary one being that there's a uniform stress present in the midsection of this bar over that span. So in the 3-point bend test, the load distribution is more triangular, and so you only really have the maximum stress at one point. In 4-point bending, we have a uniform stress over that span S. Both of these kinds of bend tests are useful for characterizing ceramics. A tensile test is not as useful for ceramic materials, but a bend test allows you to determine how this will deform.